Okay, good morning, good afternoon, good evening, depends on where you are. It's my pleasure to introduce the distinguished lecturer today, Professor Sharon Hu. Yeah, she received her PhD degree from Purdue University, and she is currently a professor with the Department of Computer Science and Engineering in University of Notre Dame. And her research interests include computing with beyond CMOS technologies, low power system design, and cyber-physical system. She is very well known in our area, and also she already did several very famous research, and she ever received best paper awards from DEC and ISLPD, and I think most of you also know that she was the general chair of DEC, and she's currently the editor-in-chief of Asian Translation on Design Automation of Electronic System, TODES, and she was the chair of ACM6DA. Yeah, I think she's very well known in our area, and today she will going to talk about in-memory computing with associative memories across their perspective. So the time is all yours, Sharon. Yeah.
Okay, great. Thank you very much, Zhongyi, for that nice, generous introduction. So again, repeat the same thing. Good morning, good afternoon, good evening, depending on where you are physically right now. It is my pleasure to share some of my exciting research recently in-memory computing with you all. So in this seminar, I would like to discuss a particular in-memory computing core, use it as example. It's called associative memory or content addressable memory, and especially from a cross-layer perspective, from devices to applications. And they'll specifically use an emerging technology called FeFET to illustrate how to maximize the application level benefits. And I want to graciously recognize or acknowledge all my collaborators and my wonderful students who have done a lot to this work. Let's see why my screen is not moving.
Yeah.
Okay.
Okay.
Yeah, good. So many of you probably already know, since you're here, that dealing with data transfer is a big challenge in many types of applications. I show some examples here. And these are called data intensive applications. So without going into details, I'll just quickly mention to me, there's three key major concerns associated with data transfers. And of course, the latency and throughput takes lots of time to fetch and store large amount of data. And secondly, energy is a big concern as well. This is a table we got from Horowitz, and it shows that transferring data is a lot more costly than operating on the data itself. And transferring data also have some security concerns, and there are other challenges. So I know there's lots of different ways to define what is in-memory computing. So I'll just show you what I consider to be in-memory computing. So traditionally, we have the CPU, we have the memory components. The memory components tend to be vague here. They can be SRAMs, DRAMs, non-volatile memory, whatever. And the key is you have to move the memory information in the memory to the CPU to process. Now there's also so-called near memory computing. So near memory computing, where the processing units can be very close to the memory components. And typically the processing components in the near memory computing setting, they tend to be more complex. Now for in-memory computing, I'm referring to the type of architecture that the processing unit is inside the memory component. Now they can be two different kinds. One is you have the processing unit inside the memory array itself, in the memory cells. And the other is having the processing unit on the boundary or on the peripheral of the memory arrays, but it's still inside the memory component. So immediately you can see that this in-memory computing can be very effective in reducing data transfer, but there are lots of challenges to design such a unit. Now, when designing these in-memory computing fabrics, we face lots of challenges. So from the bottom-up perspective, start from what choices of memory devices you should pick. Then what are the circuit level? What are the type of circuits you want to use for this in-memory computing fabric? And then, of course, how do you construct the architecture of this? And on the top of it, what is the best algorithm that can map into these architectures well? And at the end of the day, we're talking about accelerating applications. So what is the application benefit? So you can see that there's lots of choices and lots of decisions to be made. Now, it's also important to examine the problem from a top-down perspective. Depending on the application level requirements, say energy performance, one may choose one architecture or one device over the other. So in the rest of the talk, I would like to use one type of AMC core to illustrate how the choices at different levels, they interact with each other and how to get the most out of these. So the specific AMC core I will focus on is called associative memory or content addressable memory. So I'll use these two terms interchangeably. Now, here I'm using a really simple example of a associative memory called ternary content addressable memory to show you what I mean by this associative memory. And basically, you have data stored inside the memory array. And in this case, I'm storing ones and zeros or don't cares. And when the query comes, the query can be 1, 0, or don't care as well. In parallel, it searches the entire array in one shot. And it basically compares bitwise data. And if every single bit is a match, then we call that result is get reported. And that's we call it a match. And the other ones are not match. So Tcams are widely used in, or has been widely used in high associativity caches and network routers whatsoever. Now, Tcams has a challenge. The CMOS design can be quite costly. So these, again, it also has many other applications, which I will show later. But that's the concept of associative memory, basically search, supporting all sorts of searches. Now, I talk about the CMOS implementation can be expensive. There are many emerging technologies, especially non-volatile memory devices. They can also offer really lots of new opportunities for build compact and low energy ternary content addressable memories or associative memories. Now, this means there are lots of circuits, architectures options as well, given all these new devices. Now, at the same time, there's lots of growing data-intensive applications I think we're all aware of. And associative memory actually can be very beneficial to many of these applications I'm showing here, machine learning, neuro-inspired computers and bioinformatics and so forth. So given all these exciting developments, the design space again for AM is very large. So we need really a cross-layer approach to get the best out of these solutions. So the rest of the talk, I'll use a specific device called FeFET, and I'll show you a number of examples of how we can design or adopt this cross-layer design for this in-memory computing concept. So for those of you who don't know FeFET, I'll do a very quick introduction. So FeFETs are made of ferroelectric layer, but made of incorporating a ferroelectric layer in the gate stack of a CMOS device. The ferroelectric layer also referred to hafnium oxide. Now, by properly selecting the thickness of the ferroelectric layer, the device can exhibit hysteretic behavior, okay, like this. So in that sense, it's a memory, and it's actually a non-volatile memory. And this has been experimentally demonstrated. The data is experimental measured data. Now, here I show a global foundry chip that's fabricated on 28 nanometer technology for the FeFET-based, what they call it, ferro memory. All the major semiconductor companies, such as Intel, TSMC, Samsung, they're all looking or researching this device themselves, as well as supporting academic research. And we actually have such funding through the US JUMP program, collaborating with lots of these companies. So here's how FeFET works. You first use a reset voltage or program voltage to reset the device. Then you can use different levels of erase voltages to set the VTH or threshold voltage to different values. Okay. Then for different VTHs, if you apply a small read current, then different levels of current can flow through the device. So here I show a two level of FeFET VTH, two VTH levels here. One is high, one is low VTH, and you can see that it distinctively have two states. You could also have multiple states by using different erase voltages to program it. And if you are paying lots of attention, you see that the two devices have different sizes. So to get the multiple states, you do need a bigger size, which I'll come back later on to tell what does this all mean at the circuit and architecture and application level. Now, I would say that there are some other distinctive advantages compared to other non-volatile memories, such as high I-on, I-off, and also has a 3 terminals, so make the circuit design quite interesting. Okay? Now, device people are actively working on scale down these devices to smaller sizes. Just like any other emerging devices or any other nanoscale devices, FeFET also suffers from non-linearities. For example, I show here is a device-to-device variations. Recent work we showed that without write verify, you can see that if I want to program the device into 8 states, there's quite significant overlap. If we use write verify, then the overlap is substantially reduced. Okay. So the variation behavior also depends on the size, which I mentioned before. Now let's look at how do we use these devices at the circuit and architecture level, especially for building content addressable memories. So I talked about Tcam before. Here I just show you another way of looking at the Tcam design. For this particular type of Tcam I showed you here, you see that the rows that has all green ones, that means every single cell is a match. Then I'll put that line as a match. So we call this exact match type of Tcams. Okay. Now, I said before, it typically takes quite a number of transistors. Typically takes 16 transistors or CMOS transistors to implement the Tcam cell. Most recent work from University of Michigan used the 12 transistors to implement the Tcam cell based on CMOS. Now, in our work, we propose a 2 FeFET based Tcam cell. So it's really compact. But just like most other Tcam cell designs, it's used at pre-charge stage. We also propose another Tcam cell design. In this case, it has 2 transistors as well, but one is a FeFET, one is a CMOS transistor, and it has a little more complex sensing circuit at the match line level. For this design, however, we don't need a pre-charge. And it also has 1 fewer FeFET. So it has some advantages, but there's also some disadvantages. So in a sense, there are quite different ways you can design these FeFET-based Tcam cell. Now, just quickly go over of how the Tcam cell really works. Here, I have the two cells again. So we typically program the cell, one into a low VTH state, one into a high VTH state. Suppose this cell stores 1, we program it to store 1. If the query is also 1, then both of these input voltage or search line voltages, it's going to lead to low currents, as I shown here. So in this case, if I charge match line to high, there's no discharge current or very low discharge current. So the match line remains at high. And so that's a match. Now, if the cell stores a 0, you see that now I have the stored VTH values flipped. Now, if I use the same query, we can see that one of these devices, which is the low VTH device, is going to conduct. So it has a large discharge current. So match line now will become a 0. So that's how the T cell, the Tcam cell works. Now, you say, yes, it is compact. How does it compare with other type of Tcam design? So there are, FeFET based, besides FeFET, there are RRAM based cell design, PCM based, MTJ based, and of course the CMOS. So we did a comparison. This is using a radar chart to show the different figures of merits, comparing all these 6 different kind of Tcam cell design. So as can be seen in this case, the FeFET, the red box, is it outperforms other devices, all of these metrics except the R on, R off compared to flash and the CMOS based. So in this sense, it's actually quite a good design choice. Now you might see that the improvement may not be that huge, but actually this is a log scale. So just keep that in mind. So I mentioned about exact match. Now the same cell design can also be used to detect what we call the degree of match across a whole array in parallel. So consider this Tcam cell with data as shown here. So this is what is got stored. If I use this particular query, you can see that the word 1 has more mismatched cells, right, than word M. So in that sense, the current that flowing through the word M for the match line discharge current for word for MLM or match line M's match line, it has lower discharge current compared to the word line 1's discharge current. Okay, so with that, if we sample the match lines at a particular time, then the match line for M's word will have higher voltage than the match line on the first word, right? So in this way, by looking at the voltage levels of the match line, we can actually detect the degree, or we call it the distance of matching. So in this case, the match line M has a distance of 1, and the match line 3 has a distance of 3. So when we say distance, you probably can see immediately that this is what is measuring what is we call the Hamming distance, okay? So this will become important later on. And this type of Hamming distance and measuring the degree of match actually can be very useful in, say, nearest neighbor search type of applications. So in general, I talk about exact match. We can also use that degree of match measurement I just told you to design what we call the best match, meaning that we find the row or the word that has the minimum number of mismatched cells. So that's a best match. Or we could also set a threshold so that, let's say the threshold is 2, we have 2 of them. We'll call them all match. So there are different type of matches. And it turned out that the same Tcam array or same Tcam cell design, they can all accomplish this different type of matches, but the difference is in the sensing circuit. I will skip the details of how the sensing circuit works. And if you're interested, you can look at our work and also some other works I put down here. We have experimentally validated the degree of match operation using the Global Foundries chip. And here is a small, relatively small array. This is the limit of our testing equipment. And here we test a 1x6 Tcam array. And all the cells are initially set to 0. Then we change the query by increasing the number of 1s in the query bits. And as you can see that as we increase the number of 1s, then the mismatch bits increases, so you can see the discharge rate increases. Now, if we extract the discharge rate, looking at the derivative, we can see a simple linear relationship between the discharge rate and the number of mismatch bits. Okay, so this is then we design a good sensing circuit to sense the difference. Now, some NVM or some non-volatile memory devices also exhibit multiple states, like, for example, MRAM I showed here. I also mentioned earlier that FeFET exhibits multi-bit states. And in fact, there are also experimental demonstration that FeFET can also exhibit some analog type of behavior. So you see that there are lots and lots of states. So the question is, can we exploit this type of design to design other type of associative memories? And the answer is yes. Okay. So in a recent paper, a group from HP has introduced the concept of analog CAM. And this analog CAM design uses 6 transistors and 2 RRAM devices. The work has been experimentally demonstrated on an array at the array scale, so it's a really nice piece of work. Now, about the same time, we also considered a ACAM design using FeFET. Now, in this case, actually, that cell I just showed you, the 2 FeFET design, can also be used for doing ACAM. The only thing is now the FeFET will have analog states of VTH and VTH sets. Okay, so this is a very compact design. So let me briefly talk about how this ACAM works. So in the ACAM cell, we set the 2 FeFETs, one to a low VTH level and one to a high VTH level. And this high and low VTH level in each cell actually defines a range. So you see that I use the blue, I use the red. So for example, in this case, this cell N has 0.3 volt as the low VTH value and 0.9 as the high VTH value. Now the query is also an analog signal coming in. Okay, so when it's coming in, now depending on whether it's in the range or out of the range, the discharge current will be different. If you are outside the range, it will have large discharge current, as I shown here. If you're outside the range, you have large current. If you're inside the range, the discharge current is quite small. So again, then by detecting the discharge, the current on each of these match lines, then we can tell if a particular word is a match or not match. In this sense, if that word is inside the range of the stored cells. Okay, so here I show this is a match one and this is a mismatch one. Now we'll show later that ACAMs can be quite useful for certain applications. Okay. Now, we have also experimentally demonstrated this ACAM functionality. This work, the experimental demonstration, is by my collaborator, Kai Ni, who is at Rochester Institute of Technology. Okay. Now, I've mentioned before that there are some challenges with all these devices, so specifically talk about device-to-device variation. So if you have these device-to-device variations, they could make these make it difficult to separate all these different VTH values. And so that's one challenge that ACAM has to deal with. Now, another challenge that ACAM cannot do is it cannot really do this, what I showed before for the Tcam, that best or threshold match. So to address these 2 challenges, we propose another type of cam. It's called the MultiBit Cam. So it's kind of between the ACAM and the Tcam. So in the MultiBit Cam, again, in the cells now, we store distinctive states. Okay, so in this example, I showed 4 states. So basically it's a 2-bit MCAM. Now, then the query will also comes in as a voltage within a particular range. Okay, so you hear the query is also takes on one of the 4 states values. Then we do the matching here in parallel. And you can see in this case, again, we have this word, the last word is a match and the first word is not a match, okay? So here, the example I showed you is an exact match. But it can also support best match and threshold match using the sensing circuit that I have shown before. Of course, the requirement for sensing margins will be more demanding, okay? The MCAM functionality, we actually demonstrated this functionality experimentally with a small array using the Global Foundries FeFET memory chip. So here I showed you 8 different states. So you probably say, oh, see, they have still quite some variations and stuff. But it turned out that if I look at the application level, this is a particular application that I'm not going to go into detail at this point, but I want to show you here is I have the experimental data in green bar and simulation data in the kind of orange bar, and you can see that at the application level, they actually gave pretty close accuracy. So this makes us feel like this MCAM design can really tolerate some of these device level variations quite well. Okay. Now, I want to say a few words about this best or a best or threshold match. And this is an interesting concept called distance functions. So when we measure that degree of match, we actually have a concept called this distance function. Now, as you know, that similar to other CMOS devices, FeFETs also have 3 operation regions, right? Cutoff, linear, and saturation. It turned out that if we operate the FeFET at one of the two the different regions, they actually give us different type of distance measurement. So if it's a linear region, it has a function similar to something what we call the sigmoid-like function. And if we bias the device at the saturation region, it actually measures the distance like a Euclidean distance, or we call it squared Euclidean distance. And all these different functions actually can be quite useful for different type of applications. Now, to show you what is the difference in terms of these distance functions, I use a heat map to show this. And this is for 2-dimensional distance vector. So these are all measuring distance from vector 1, 1. So you can see these are the distances for the 2 different dimensions. You can see that sigmoid measures this type of distance. So here, when it's close to here, this is a closer distance. And if a Euclidean is this type. And you might also be familiar with cosine similarity. That's another distance metric, and that's measuring this type of distance, right? It's showing that anything along the diagonal line is a shorter distance. So different application actually may benefit from these distance function, different type of functions. And I'm going to show in some applications that what they also mean at the application level. So with that, I also want to just quickly mention that when you use these different regions of operations, they also have an impact on latency and energy, besides the accuracy, as I mentioned. Actually, we also showed that this type of designs, these distance metrics, they're also applicable to a flash-based CAM design, and we recently published work a couple months ago. So showing you all these different type of CAM designs, I actually skipped some other types that we also have worked on. But let me just take you to the application level and want to show you how they can impact the application level accuracies and other figures of memories. CAMs actually are very useful and for many applications. Here, I just highlight a few. For example, we can use it to implement what we call the attention memory in many of the neural network structures, and in particular, in few-shot learning that using memory augmented neural networks. And it can also be used for accelerate hyperdimensional computing. This is another quite powerful neuromorphic models that helps to do classification and so forth. Recently, there has some work that using the content addressable memory to implement vector processing in parallel. And this work was by our collaborator at Cornell, and it's published at a very recent paper. And we're actually working with them to see how these type of CAM designs that for different technologies that can be used to implement their architecture. Some other works I mentioned, like bioinformatics, that does a lot of matching. So there, the CAMs can also be very useful. And our recent work has shown a CAM-based DNA read mapping accelerator. And all of these different works, actually, they can use different type of technologies, and different type of CAMs, different type of distance functions. So that's make it really interesting to explore the design space. So I'm going to use one example, this few-shot learning, to show you how we can use Tcams and MCAMs, and that I talk about, right, multi-bit and ternary bit, to show for accelerating this few-shot learning. And if you're not familiar with few-shot learning, so I'll go very quickly about what it is. So we know we humans can learn very quickly from a few samples, but typical neural networks are designed, they need large number of training samples. So there are new, or I shouldn't say that new, in the machine learning community, it's not that new anymore. It's in the last, I would say 4 or 5 years, people have started looking at few-shot learning. And one particular few-shot learning model is called memory augmented model. Let me just say, so if I give you these 4 dogs, after you look at it, if I give you another dog, you probably can quickly say, oh, I think this is this type of dog, right? That's what we are good, humans are good at learning from very few samples. And for using the few-shot learning setup, or in this particular memory augmented neural network, we can use a trained neural network to learn the features and then use an attention memory to store the features we have learned. Okay? And this is the kind of, we call it meta training stage. And after you have the meta training stage, then you can also use a few, what we call the support images, or few samples, few vectors, few samples. In this case, I only show 1 sample, so we call it one shot. And now, then we, again, these new samples, they go through the neural network, extract the features, and then also get stored in the embed in the attention memory, just like the other features we have learned. Then when the new query comes in, it can actually, again, go through the neural network and then go into this attention memory to see which feature vectors are nearest to this. And the nearest ones then will be reported as the class that this dog belongs to. Okay, so in this case, we kind of overcome this problem of what we call the catastrophic forgetting. So we use a few samples, then we can learn new classes, then we can inference the new classes quickly. Okay. And in this case, actually, this is just one shot, like I said. Okay. Now, to implement this memory augmented neural network, of course, when they first started, they used a GPU to implement it. The GPU then interacts with external memory, where I'd call it this attention memory is implemented. Now, of course, we all know this suffers from data transfer problem. Now it turned out that we can use the ternary content addressable memory to implement this attention memory. And in this case, we could use what we call like a locality sensitive hash to help improve the accuracy. I will not go into the details on this, but the key here I want to mention is using this Tcams, we basically using the function called best match, right? We talk about best match, so this is using the best match. Now, we can also use the MultiBit or MCam to implement this attention memory. In this case, we don't need a locality sensitive hashing anymore. And all we need is just directly implement the attention memory using the MCam. And again, we use a function of a best match. So if I look at this different designs, so immediately you can see that they could have a huge design space, like I said before, for whenever you use content addressable memory. And in terms of figure merits, we have accuracy, energy, latency, area, etc. So what are the design spaces, right? Which type of cams you should use, which type of functions, and what type of sensing circuit, and what devices. And if you decide to use FeFETs, we also have lots of design space, and even within the FeFETs, in order to, for example, in order to overcome device-device variations, we have to look at the device areas, we have to look at how to program, and so forth. So don't need to go into the details, but I'm just showing you the design space is huge, and a cross-layer design is really important in this type of practice. So without going into the details how we did all these explorations, let's look at some accuracy result, which shows the different choices can lead to different accuracies. Now recall I said cams can implement different distance functions, and they can also have variations. So in this case, I plotted accuracy versus standard deviation of variations, of device variations. Now we consider the GPU. This is a floating point GPU accuracy. Okay. Then we look at 5 different CAM implementations. 2 of them, the 2 dotted lines and dashed lines, they are MCAM implementations. They are using 512 dimensions. We call it 512 columns. And one of them implements the sigmoid-like distance, and the other ones implement the squared Euclidean distance. Okay, and then we have 3 Tcams. One Tcam have 512 columns, and then the other 2 have increasing the number of columns. So one thing you see that if there's no device-to-device variations, several of these designs have relatively comparable accuracy with the GPU implementation. However, if we have device variations, then you see that they drop off rapidly. Now, if you look at the variations, if you say, what does variation depends on? Actually, fundamentally, the variation depends on, we call it number of domains in a device. And the number of domains, you can think about it without going into physics, think of it as the atomic size in the ferroelectric material. So the more domains you have, typically the larger the device would be. Okay, so in this case, you can see that for larger devices, then the variation will become smaller. Right? And also, if you do verify, then also the variation also becomes smaller. Now, suppose your application says, I can accept about this, this level of accuracy, let's say, and then we need 100 millivolt standard deviation. In this case, you can see that coming back to here, we see only these type of choices are valid, and the other type of choices are not valid, right? So this tells us what are the dimensions and what are whether we need to verify or not in order to satisfy this particular accuracy requirement. So at the end of the day, when you have larger domains, you have larger cell areas. And though it helps on the variation side, it does impact the parasitics. So that means it can lead to higher energy and latency. So let's look at what does that really mean. So here I have accuracy directly versus the area got plotted here. Okay. Again, I have the MCAMs, I have the Tcams of different sizes. Both MCAMs are based on 512. And the Tcams, one is 512, one is 248. So immediately you see that for the same size, same area, the Tcams with 512 design is just not going to cut it in terms of the accuracy, right? Now, especially when you don't do verify. Even if you do verify, it still doesn't help a whole lot. However, for the other designs, much larger Tcam designs or MCAMs or designs, the accuracy are become similar. Okay. However, if you directly compare at about the same accuracy, the 3-bit Tcam, the 3-bit MCAM actually have about 2x area reduction compared to a Tcam design. So this shows that you do have nice trade-off between whether you want to use Tcams or MCAMs. And here is a reflection on the accuracy versus energy, search energy. Again, one is for without verify, one is with verify. So this similarly that you can see the 3-bit at approximate similar accuracy, the 3-bit MCAM has about 4x energy reduction than the Tcam based design. Okay, and also I also plotted both the Euclidean distance and sigmoid distance. So the sigmoid is the blue ones, and the Euclidean is the red one. So again, you can see that they offer similar accuracy, but the sigmoid design consumes less energy because it's operating at a relatively low current region, right, in that linear region. So this is one example. And I have lots of other examples I'm not going into, hyperdimensional computing. That's also very interesting work that we have recently published at ISLPED. But I do want to show you another quick example. This work is really brand new. The manuscript, we're still preparing it. And this is using ACAMs for implementing decision trees in random forest. So decision trees are the kind of the main component, the core component in random forest. And random forest, though it may not offer as high of accuracy as, say, deep neural networks, but they are sometimes preferred because they have this nice property of can be more explainable, right? So lots of people are working on this random forest based machine learning models. Now, I just showed you what is the decision tree is. So immediately, if you're familiar with GPUs, you know that implementing these decision trees in GPUs are very expensive because all of these are branches, so they can be quite, cost lots of data transfer. Now, it turned out that we can actually use this, the ACAMs to implement this decision trees very efficiently. So in this example, what I've shown you, let's say consider one decision tree model here. So let's consider these are ACAM cells. So for each branch, for a branch in the decision tree, let's say this x1 less than theta, then all we need to do is we just program our ACAM cell. So for the low VTH, we program it to the lowest voltage, lowest VTH possible. Okay, and then for the high VTH FeFET, we program it into the VTH of sigma. So in this case, so this is represented by this red line. Okay, so now if a query data comes in, if it falls in between this range, meaning if it's less than theta, then it'll be a match. Okay, so other branches can implement the same way. Now, if we match the entire tree, basically for each path, you think about the tree as a path one, each path will basically correspond to a row in a ACAM array. Okay, and so here I have 3 paths, then I have three rows. So if you have all the rows are, all the cells are matching within a single row, then that path is a match. So that means that query belongs to this particular path. So that's a successful match. And how does this really behaves in a real data set? So here we examine the accuracy first. I think I probably, oops, I didn't do the animation, but let's look at the left one. This is the accuracy versus different implementation versus the first one is this one is versus the variations. So this shows the FeFET. This is a 3-bit FeFET ACAM design. And here, this is a LSTM based design. And here is a GPU-based floating point design. Okay? And this is for a called the SEMG data set. This is for hand movement recognition. This is a pretty well utilized data set for random forest. So first you can see that this design is in terms of accuracy, if at very low sigmas or very low variations, the accuracy is actually approaching the floating point implementation. And even with very large variations, it's still pretty close to LSTM. And actually lots of them all performs LSTM. So it definitely, in terms of accuracy, is quite good. And now then for energy or latency, or in this case, I'm plotting energy versus latency. So here's where the CPU implementation lies. And you can see that I actually compared with the RRAM design, the ACAM RRAM design from HP with our FeFET design. So they both outperform CPU significantly, but with FeFET, given its nice properties, it actually has lower latency and lower energy. So I showed you all these examples, and I just want to kind of highlight, in order to do all these design space exploration, we really need some tools. So lots of work when we initially started, they are mostly based on hard works of H-spice simulation, and then high-level simulation and so forth. Currently, we are working on a tool called the EVACAM, and this is a cross-layer framework trying to evaluate CAM-based system from devices to applications. And it considers all the different type of CAM designs I have talked about, BCAM, Tcam, MCAM, ACAM, etc. And also consider different type of matches, and as well as different type of distance functions like sigmoid, square, Euclidean, etc. It starts with the subarray evaluation. And the subarray evaluation, it takes input cells and other information. I'm not going to go into the details due to time. So it takes a device level and cell level information, it extracts the array level evaluation. Then that gets fed into the array level evaluation. This is the bigger, multiple CAM arrays. And again, that will take certain input from the users in terms of the array level implementation, banks, peripherals, etc. And that then get fed into the application level evaluation. Application level will need its own inputs, like how many reads, how many writes, or in terms of the matches, what is the average number of mismatch bits are tolerated, and what are the memory specs, etc. So that's the evaluation. So it can give you the figure of merits, like I showed you, the energy and delay, etc. And then eventually we want to do this algorithm and architecture co-design so that we can explore the entire design space. And for this, of course, we'll need objectives and constraints from the users as well. We have a preliminary tools, and if some of you are interested in working with us on the tools or using the tools, you can contact me. So let me just wrap up. I have shown through a specific device and a different type of associative memory designs how the importance of conducting a cross-layer design. My example is from the device and to the application level, but it's equally important to do from top down. Application level needs can help guide this research focus at the lower levels. Okay, so for example, one important question that we, together with our sponsors, at SRCs and different companies, we are asking this question of what is the, how much accuracy degradation can be tolerated for improving other figures of merits like energy and latency. And this is actually very much of a, application level driven, and then trying to reduce to the hardware side. Okay. Now, I would say in-memory computing has huge opportunities in terms of reducing data transfers, overhead, offering high throughput, these parallel searches, and also data retention, especially if you use non-volatile memories, etc. Now, of course, it also faces lots of challenges, right? I list a few of them here. How do you balance the density and functionality? How do you make sure the peripheral overhead is not overwhelming the memory array itself? What is the right memory hierarchy? I didn't go into the details of how do we organize all these CAM arrays so that they can support really large arrays. And of course, as always, very importantly, sometimes we hardware designers tend to downplay a little bit, is the programming model and support. So lots of opportunities, also lots of challenges. So I'm hoping that many of you also are excited about this work and join this effort to push this frontiers of this research area. So with that, I want to acknowledge all my collaborators, and I can answer questions. Thank you.
Okay.
So I see there are questions. Hi.
Yeah, we actually have a couple of questions. Thanks for the comprehensive presentation. Yeah, you go from device all the way to the application. You talk about the cross-layer optimizations. That's very impressive. Yeah, so we have I think we have 5 questions.
Yep.
Can we see all of them? I think 2 are from the chat box, 3 are in the
I see.
another Q&A
Great
box.
Q&A. So let me take I think the last question from the chat box is asking, it seems that deep neural networks are more dominating machine learning methods. Why aren't you focusing on CIMs for DNNs? Very good question. So CIMs, in this case, I think you are referring to crossbars. And we do have work in the crossbars. And as you know, that's also a very, very active area. You know, people look at crossbars using RRAMs, and we actually use crossbars to build, we use the FeFETs to build crossbars as well. And I feel that's a very, I shouldn't say well studied, but that's very active. Lots of work has been reported, but I feel not as much work has been reported on this search operations, you know, associative memories. So that's why I'm focusing on this and not discussing that work. But if you're interested, I will definitely be able to share some of our FeFETs related, both analog and binary or multi-bit type of crossbar designs for accelerating DNNs. Another question on the chat box is, I'm curious about how much did the MCAM speed up compare with the traditional memory usage on decision trees, or what is the advantage of using MCAM rather than traditional memory or other CAMs in decision trees? I think my, let me see if I can go back to this plot here. This actually does show the CPU design here. Oh, now I see your question. Maybe you're talking about if I use CMOS to implement a content addressable memory. I'm not exactly sure, but so the question can be answered in two ways. First is, if we're just talking about traditional memory in terms of just memory itself, not content addressable memories or associated memories, then the CPU data is right here. That's using the memory. Now, if we use CMOS to implement the content addressable memories, one thing is you can see that with CMOS, with this only on-off state, it cannot really implement this ACAM or MCAM efficiently. So that's why we didn't compare, because it cannot do. Now, for Tcams, yes, it is possible to use CMOS to compare. And in general, the conclusion would be CMOS will be a little faster. And in terms of search, their energy could be similar if we only consider active search. If we consider standby and standby power, then these non-volatile memories also can outperform because it has very low leakage. I hope I answered that question. So let me go to the questions in the QA. Can hardware accelerators based on in-memory computing be used as functional blocks in coarse-grained reconfigurable computing? I'm not exactly sure what is meant by reconfigurable computing here, but these in-memory computing blocks can definitely be used. If you think, let's say if I have an in-memory, let's say I have these crossbars or AMs in a together with a FPGA type of framework, I think that should not be a problem. I guess the only thing is we need all these devices or all these new devices to be compatible with CMOS, which is true. RRAMs and FeFETs both are compatible with CMOS, so they can definitely use in this coarse-grained manner, integrated with other type of reconfigurable fabrics based on MOS devices. Another question is, can platform-based designs, say from Alberto's group, be used instead of top-down or bottom-up? The platform designs, I actually know these work really well. They develop, I think, long time. I think you're referring to something like a Ptolemy type of works. I think if you model it correctly, then we can leverage that type of framework. And the key is in the modeling. So I always tell my students as well, if you use certain tools, you have to understand what the type of input, what type of inputs the tools support. And then if you can model your problem so that the type of tools can support, then it should be good. I think that this is a very good question, and we can definitely look into how to integrate some of these like EVACAM type of relatively lower level tools to the higher level tools. I think the platform design, they're actually talking about lots of the hardware software co-design in terms of you have multiple cores, you have multiple accelerators, and how do they all work together? And instruction set architectures, yeah, PyTorch. If so, what should be chosen as a platform or set of platforms? Like I said, I think how to use that type of these platform-based design frameworks with these lower level things, I think there's some integration issues we probably need to resolve, but that's definitely an interesting direction to look into. In terms of machine learning models, these are, all of these machine learning models, we call them as they are the application levels. I think what we tend to use them for is we use them to validate some of the accuracy stuff. And then, however, we still need tools to extract the operations that's really needed in order to feed it into these tools like EVACAM. So we still need other tools to help on that side. Here, yeah.
I think the Xunjiao as at the very first beginning.
Oh, did I miss something?
No, I think he or she will just put here. Yeah.
Yeah, I see Xunjiao's question here. What is the manifestation of device nonlinearities in FeFET memory? Random bit flips, ducket faults, they're different. Okay, so what type of non-idealities? Yeah. So I talk about the variations. Random bit flips, if this would depend on temperature effect, you might have random bit flips. And actually, these are all very, very good questions. Radiation effect, temperature effect, and also reliability, in terms of you use the data for while the retention. These are all effects that could impact the behavior or the storage. So in a sense, if you put the device into high temperature, it will eventually, the VTH going to change. I don't think it's necessarily random, but if you, it could have random, but right now I don't think it's that random. It does have interesting patterns. And actually I have a couple of ongoing collaborations with people at different places that studying these effects. We have a recent paper on studying the temperature effect on FeFET. So if you're interested, I would be happy to share the paper with you. Another interesting part is the retention. After the device has been used for a while, it may not be that reliable anymore. Let's say if you store weight in there, after you store a particular VTH, after you use it for a long time, for a while, and you keep reading it, then that VTH could drift. Okay, that type of drift might also have some interesting behaviors that we could study. Let's see, I got a couple more questions here. Let me scroll down here. I know this Giovanni asked, I asked a couple of questions from you, so let me just go down to the bottom one and I come back to you, okay? When the standard deviation is high, that means we have a big difference between the minimum and maximum. What does it mean in your application in terms of hardware design? So when we say the standard deviation, we actually meant when you set you want a particular VTH. Let's say you want the threshold voltage to be at 0.5, but then when you write it, you don't get 0.5. You will get, say, 0.45 or 0.65. It could be on either side, right? Now then, what it means on the application side if your MCAM design, it can tolerate, your range can tolerate that variation, then you are okay. You're still within the range. If it's outside the range, you remember I have these little squares. If it's somehow your variation takes your VTH to the next neighboring VTH range, then that means you have a wrong weight, if you want to consider that, but you have a wrong value stored in the memory. Now, the fortunate thing is some of these machine learning applications, like for example, one we have spent lots of time on is hyperdimensional computing. They are naturally good at tolerate some of these some of these little mistakes, because it's using a really high dimensional vector to represent data. So in that sense, some of the models, some of the application machine learning models, they can tolerate some of these weights variation to a certain extent. But then if you have lots of variation, if they're big, then you will definitely have serious problems. So like I show here, right? For example, in this slide, I'm still having up here. If you have a variation of 0.2, meaning you have 20% of deviation from your desired memory window, you can see how this accuracy degrades. Now, so I hope that's the impact. Now, in terms of design, then we have to think about how to accommodate, right? One way, of course, is at the device level or at the circuit level, we use write verify to reduce it. Then other ways, then we actually have to think about, in terms of online training. Maybe we know that we cannot write accurately, then maybe we can exploit some of the online training so that it can learn its mistakes and they can make use of the mistakes to still improve the accuracy. So this is kind of really interesting, perspective from the application level. Application level, it doesn't care whether you have a mistake or not at the device level. All it cares is you have a good accuracy. Okay, so using some online training could help. I think there's some of the work has already been done, say for crossbar-based designs, and we can do the same thing for the CAM-based design as well. So let me move back to the couple questions from Giovanni again regarding standby NVM-based MCAM, ACAM. Can we use them for intermittent computing, such as they switch on and when needed? That's also a very good question. Yes, we could use them for intermittent computing, but currently most of the non-volatile memory has one drawback, and that is they are expensive to write, right? Even without verify, they tend to use higher voltage, and they also tend to have longer write time. And that's one place they cannot beat CMOS yet. RRAMs, FeFETs, they all have this problem. So if, in that sense, unless your intermittent time is really long, you have to keep writing them, then that's not worth it. Now, talking about different technology choices, MTJs, especially these SOT MTJs, these are new magnetic memories, using the tunnel junction. Those are actually can have much lower write voltage, and I think as MTJ-based CAMs, which we are also working on with a couple of groups working on these devices, they actually can be a nice device choice for this type of application, where you need lots of write, but you also can have, you also want some non-volatility, then MTJ type of device could be a better choice. But MTJs actually have its own challenges because its TMR ratio is relatively low compared to RRAMs and FeFETs. It'll be hard to implement ACAMs and MCAMs. So they're good choices for Tcams. So all these are very, very interesting design choices.
Yeah, I think you answer all the questions. Yeah,
okay.
Thank you. Yeah, thank you, Sharon. I think this is a very good topic, and I think some of my friends are working on this ferroelectronics. I think recently there are some new research trend are using I forgot the name. It's called the van der Waal. wonderful ferroelectronics. I'm not sure if you heard about this two-dimensional. I think just
the two-dimensional material used to build ferrofets. Yeah, so that's you can see that there's lots of excitement going on the ferrofets. So if you are kind of on the hardware side, you are interested in exploring emerging devices, I will definitely encourage you to look into ferrofets. It's relatively new, but it's already get lots of support. I think, you're saying what Chongyi was saying, people are looking at the material side and people are looking at the device designs and lots of material challenges also. The ferrofets, I showed you, you say why they are not here yet. Mass production, especially using relatively lower voltage to write, is also a very not easy. And very recently, actually, we just submitted an IEDM paper that's looking at another type of ferrofets that we call the back end of a line ferrofets. So they're using a different way. Instead of integrating the ferrofets into the gate stack of a traditional CMOS, now they're building the ferrofets device using back end of a line. And they're different type of ferrofets, and that actually allows us a more better way to integrate, because that opens up the 3D integration opportunities. So again, definitely a very, very exciting area. So if you haven't looked into that, if this is a direction you're interested, definitely look into it.
Yeah, thank you, Sharon, for the wonderful talk.
Yeah,
thank you so much.
Okay, sure.
Yeah, thank you so.
Thank you all for staying over time.
Yeah, so wish everyone safe in this weird pandemic time. And also I want to announce that then for next month, so for everyone, so next month we will have another exciting virtual distinguished talk, distinguished lecture talk from Professor Sachin Sapaneka from University of Minnesota. Okay, so thanks, Sharon, for your wonderful talk. When we will record your video and for on the CEDA video library.